Have you ever stopped to think about what you're made of? It is a profound question. You are made of atoms, trillions upon trillions of them. These atoms come together to form molecules, which then form your cells, your tissues, and ultimately you. But what gives these fundamental building blocks their substance? What gives them their stuff? This substance is what physicists call mass. It is a property of matter that we experience every single moment of our lives. When you lift a heavy box, you are fighting against its mass. When you simply stand still, you can feel the Earth's gravity pulling on your own mass. It is everywhere. Mass is one of the most fundamental properties in the entire universe. It dictates how objects interact with each other through the force of gravity. A planet with more mass, like Jupiter, has a stronger gravitational pull than a smaller one, like Earth. This is why our planet orbits the Sun, and the Moon orbits our planet. The intricate cosmic dance of galaxies, stars, and planets is all choreographed by mass. Without it, there would be no structures in the cosmos. No stars would ever form, no planets would gather from cosmic dust, and no galaxies would cluster together in the vast emptiness of space. The universe would be a completely different place. But what exactly is mass at the most basic level? It is not the same as weight. Your weight can change depending on where you are. On the Moon, you would weigh much less because the Moon's gravity is weaker. However, your mass, the amount of stuff you are made of, would remain exactly the same. So the question goes deeper. Why do the tiny particles that make up everything in the universe have this intrinsic property? Why does an electron have the mass it does, and why does a proton have a much greater mass? This was one of the greatest mysteries in modern physics for decades. Understanding mass is not just an academic curiosity. Let's try a thought experiment. Imagine a universe where nothing has any mass. What would that universe look like? It is a bizarre and almost unimaginable scenario. In this massless world, every single particle would behave like a photon, a particle of light. Everything would travel at the speed of light, zipping through the cosmos in straight lines, never slowing down, never stopping. There would be no atoms, because electrons, which need to be bound to an atomic nucleus, would simply fly away at light speed. Without atoms, there can be no chemistry, no molecules, and no complex structures. To solve the puzzle of mass, physicists proposed a truly mind-bending idea in the 1960s. They suggested that the entire universe, every single cubic centimeter of space, is filled with an invisible energy field. This isn't like a magnetic field, which is strong near a magnet and weaker further away. This new field is everywhere, and it has the same strength throughout all of space and time. It was there moments after the Big Bang, and it is here now, all around you, and even passing right through you as you listen to this. This omnipresent energy field was the missing piece of the puzzle. It would come to be known as the Higgs field. The theory of the Higgs field and its boson was a beautiful idea, but for decades it remained just that, an idea. To prove it was real, scientists had to find the Higgs boson. The problem was, nobody knew its exact mass. Predictions ranged from relatively light to incredibly heavy. This meant that the search would be a monumental task, requiring a machine of unprecedented power and scale. We needed to recreate the conditions of the very early universe, just a fraction of a second after the Big Bang, when particles like the Higgs boson would have existed naturally. To do this, physicists embarked on one of the most ambitious engineering projects in human history. They built the Large Hadron Collider, or LHC. Located at CERN, the European Organization for Nuclear Research, on the Franco-Swiss border near Geneva, the LHC is the largest and most powerful particle accelerator ever constructed. It is a scientific instrument of breathtaking complexity. It sits in a circular tunnel 27 kilometers in circumference, buried 100 meters underground. Inside this ring, two beams of protons, the nuclei of hydrogen atoms, are accelerated in opposite directions to almost the speed of light. They are guided by thousands of powerful superconducting magnets, which must be cooled to a temperature colder than outer space, just 1.9 degrees above absolute zero. The goal of the LHC is to smash these beams of protons together at specific points around the ring. At these collision points, giant detectors like enormous digital cameras have been built to record what happens. When the protons collide, Their immense energy, thanks to Einstein's famous equation E equals mc squared, is converted into a shower of new exotic particles. Many of these particles are heavy and unstable, existing for only an infinitesimal fraction of a second before decaying. It is within the fiery debris of these miniature Big Bangs that physicists hoped to catch a fleeting glimpse of the Higgs boson. The energy of the collisions had to be high enough to produce such a heavy particle. Building and operating such a machine is a global effort. It required the collaboration of thousands of scientists, engineers, and technicians from over 100 countries. Two main experiments, named ATLAS and CMS, were designed specifically for the hunt. After the Large Hadron Collider switched on in 2009, the hunt began in earnest. For years, the two giant experiments, ATLAS and CMS, collected and analyzed data, working in a state of friendly but intense competition. The physicists slowly and carefully excluded regions where the Higgs boson could be. They would look for its signature at a certain mass, and if they found nothing beyond the expected background noise, they could rule out that mass. It was like methodically searching a huge dark forest for a hidden creature. The 4th of July 2012 is a date that will forever be etched in the annals of science. At CERN, an air of extraordinary anticipation filled a packed auditorium, with thousands more physicists around the globe watching via a live webcast. Fabiola Gianotti, the spokesperson for the ATLAS experiment, took to the stage first. She methodically presented the evidence, showing graph after graph, each one revealing a growing excess of events, a persistent bump, right at a mass of around 126 GeV. The audience was captivated, hanging on her every word as she built the case. Then it was the turn of Joe Incandela, the spokesperson for the CMS experiment. As he concluded his presentation, showing the definitive 5 sigma result, the auditorium erupted. Years of dedication, of painstaking work and intellectual struggle, had culminated in this single, triumphant moment. The applause was thunderous, a release of decades of pent-up hope and effort. Among the audience sat several of the theoretical physicists who had first proposed the mechanism back in the 1960s, including a visibly emotional Peter Higgs. Now in his 80s, he had waited nearly half a century to see his theory vindicated. The following year, in 2013, the significance of the breakthrough was formally recognized at the highest level. The Nobel Prize in Physics was awarded jointly to François Englert and Peter Higgs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of massive subatomic particles, and which was recently confirmed through the discovery of the predicted fundamental particle. The discovery of the Higgs boson fundamentally changed our understanding of the universe. It confirmed that mass is not an inherent property of particles, but an acquired one, bestowed upon them by their interaction with the all-pervading Higgs field. This is, honestly, a profound shift in our cosmic perspective. It reveals that the very substance of our bodies, the mass of the fundamental particles that constitute our atoms, is not an intrinsic property. Instead, it is a consequence of our continuous, intimate connection to a cosmos-spanning field. You are not just a collection of particles. You are a collection of particles that are constantly talking to the Higgs field. Our journey into the heart of matter has taken us from the simple question of what is mass to the very edge of our current understanding of the cosmos. The discovery of the Higgs boson at the Large Hadron Collider was more than just the finding of a new particle. It was the confirmation of a profound and revolutionary idea that the substance of our universe is not a given, but a property acquired through an interaction with an invisible, all-pervading energy field. This discovery completed the standard model of particle physics, providing the final, crucial piece of a puzzle that had perplexed scientists for nearly half a century. It stands as a monumental testament to human curiosity, collaboration, and our unyielding desire to comprehend the fundamental nature of reality. But this triumphant conclusion is not an ending. As is so often the case in science, answering one great question has only revealed a host of new, even deeper mysteries. The universe still holds many secrets, and the journey to uncover them has just become even more exciting. We have learned that we are all, in the most literal sense, children of the Higgs field. The quest for knowledge continues, And while the discovery of the Higgs boson marks the end of one great chapter in physics, it is truly only the end of the beginning.